Hello everyone, I'm Naoto Osaka from Cyber Agent Japan. I'm going to introduce probabilistically checkable reconfiguration proofs and prove the hardness of approximating reconfiguration problems. This is a joint work with Shuichi Hirahara. I will introduce reconfiguration problems. Suppose you are given a pair of feasible solutions for some NP problem. In reconfiguration problems, we study the reachability and the connectivity between feasible solutions and some adjacency relation. For example, we would like to know if two solutions are reachable to each other, and if so, we want to find the shortest transformation. On the other hand, if two solutions are not reachable, we may try to relax the feasibility so that two solutions become reachable. In the last decade, many reconfiguration problems have been formulated. Three-sat reconfiguration is a canonical reconfiguration problem which is p-space complete. In three-sat reconfiguration, we are given a 3CN formula phi and its two satisfying assignments, initial sigma and target sigma. Then we would like to find a reconfiguration sequence of satisfying assignments from initial sigma to target sigma. Our reconfiguration sequence is any sequence such that every two adjacent assignments differ in at most one variable. This slide shows a ES instance. The hypercube is a solution space of the formula phi. We can transform from assignment 100 into assignment 010 by passing through 000, which is also a satisfying assignment. This slide shows a no instance. We cannot transform from 100 into 111 because we must touch 110, 011, or 101. And all of them do not satisfy phi. Independent set reconfiguration is another reconfiguration problem. In this problem, we are given a graph G and its independent set of size k, initial I and target I. Then we would like to transform initial I into target I by adding or removing a single vertex, such that each vertex set is an independent set of size at least k-1. This slide shows a ES instance. We can transform the left independent set into the right independent set by removing a single vertex and adding a single vertex. This slide shows a no instance. We cannot transform the left independent set into the right independent set because we get stuck in the three independent sets in the middle. This table shows some known results of the complexity of reconfiguration problems. Typically, if the source problem is NP complete, then its reconfiguration problem is likely to be p-space complete. And if the source problem is in P, then its reconfiguration problem is likely to be in P. But there exist some exceptions which demonstrate non-trivial relation between source problems and the reconfiguration problems. In this paper, we study optimization versions of reconfiguration problems. Our motivation is the following. If we find that given input is a no instance, or reconfiguration problems of interest are p-space complete, we still want to find a kind of approximate reconfiguration sequence. Such a reconfiguration sequence may consist of almost satisfying assignments instead of exactly satisfying assignments. So let's consider relaxing the feasibility of reconfiguration problems. Max-min three-sat reconfiguration is an optimization version of three-sat reconfiguration. We are now able to use any non-satisfying assignments to construct a reconfiguration sequence. the objective function is defined as the minimum fraction of clauses satisfied by assignments in the sequence. And we want to maximize this objective. Consider again a known instance in the slide. We can transform from 100 into 111 by passing through 110. 110 is not a satisfying assignment, but it satisfies 2 of the 3 clauses of phi. So the objective value of this sequence is 2 over 3. And this is optimal. Max-min independent set reconfiguration is an optimization version of independent set reconfiguration. We relax the size constraint of independent sets. The objective function is the minimum size of independent sets in the reconfiguration sequence. Consider a known instance in the slide. We can transform the left independent set into the right independent set if we can use independent sets of size 1. So the objective value of this sequence is 1/2. Here we review known results on hardness of approximation for reconfiguration problems. By using hardness of NP optimization problems, which are based on the PCP theorem, it is shown that optimization versions of click reconfiguration, subtle reconfiguration, 2CSP reconfiguration, and Checkable reconfiguration are NP hard to approximate within a constant factor. Since reconfiguration problems are p-space complete, NP hardness results are not optimal. But NP hardness may not be directly transferred into p-space hardness. And the significance of showing p-space hardness is the following. The first is that there is no polynomial time algorithm and P is not p-space, like NP hardness. And the second is that there must be a super polynomial length reconfiguration sequence and the NP is not p-space. In fact, p-space hardness of approximation for reconfiguration problems was posed as an open problem by Ito, Domain, Harvey, Papadomitrio, Sideri, Uehara, Uno. And to investigate p-space hardness of approximation, we may need a reconfiguration analog of the PCP theorem. Last year, I proposed a working hypothesis called the Reconfiguration Inapproximability hypothesis, RIH. And assuming RIH, many reconfiguration problems are p-space hard to approximate within a constant factor, such as the reconfiguration problems of CSP, satisfiability, and graph problems. So, the central question in hardness of approximation for reconfiguration problem is whether RIH is true or not. Our results in this paper are the following. Briefly, we prove that the reconfiguration inapproximability hypothesis is true. So, many reconfiguration problems turn out to be p-space hard to approximate, which resolves the open problem of Ito domain, Harvey, Papadomitrio, Sideri, Uehara, Uno. And independently of our work, Karthik and Manulansi also proved RIH. Technically speaking, we developed probabilistically checkable reconfiguration proofs as a new PCP-like characterization of a p-space. I will explain what is probabilistically checkable reconfiguration proofs, PCRP. Similar to PCP, we are given a verifier V, but we are also given a pair of polynomial time algorithms pi start and pi goal. In the completeness case, if the input x is in the language L, then there exists a reconfiguration sequence of proofs from pi start to pi goal such that verifier V accepts every proof with probability 1. Let me use a toy example. Suppose we are given a pi start and a pi goal shown in the slide. Then our reconfiguration sequence looks like this. and any pair of adjacent proofs differs in at most one symbol, and the reconfiguration sequence pi can contain exponentially many proofs. And the verifier V accepts each proof in the pi with probability 1. In the soundness, if X is not in L, for any possible reconfiguration sequence from pi start to pi goal, verifier V rejects some proof with probability 1/2. In this example, verifier V accepts the first two proofs but rejects the third proof. Our PCRP theorem states that P space is equal to PCRP in the following sense. If a language L is in P space, then there is verifier V with logarithmic randomness complexity and constant query complexity, and the polynomial time algorithm pi start and pi goal such that they have perfect completeness and soundness less than 1/2. In this sense, PCRP characterizes the P space. Here is a quick Q&A. First, one may need any intuition or interpretation of PCRPs. PCRP can be thought of as a for-all and a co-RP type verifier. This is because verifier first guesses the index t and checks the proof pi t probabilistically. And PCRP can be compared to existing proof systems. On one hand, PCP for NEXP, which contains P space, requires polynomially many random bits, but our PCRP only requires logarithmic randomness. On the other hand, the standard PCP for NP does not use non-determinism, unlike PCRP. In this paper, we show that for all quantifier of PCRP cannot be replaced by any randomness. And second, one may also wonder if linear gap amplification can be adapted. There are some partial progress on this approach, but it still fails to construct linear-style PCRP. We also review related work. Probabilistically checkable debate is a different PCP-like characterization of P-space. And this can be used to prove that a quantified Boolean formula is P-space hard to approximate within a constant factor. And the optimization variants of reconfiguration problems often refer to the shortest sequence and incremental optimization, but these variants are orthogonal to this work. In the remainder of this talk, I will give a proof sketch of PCRP theorem. Our starting point is a problem called succinct graph reachability. In succinct graph reachability, we are given an exponentially large graph and its two vertices, v start and v goal. Then, we are required to find a reconfiguration sequence of edges from the self-loop at v start to the self-loop at v goal. Each pair of adjacent edges in the reconfiguration sequence must be adjacent in graph G. And this problem is known to be P-space complete. In this example, we start from the lower left vertex. We move y to the right vertex. We then move x. We next move y, and we also move x. And we finally arrive at the lower right vertex. Now we would like to construct a probabilistic reconfiguration proof system for succinct graph reachability. There are two issues specific to reconfiguration. First, we have to ensure that any adjacent pair of proofs differs in at most one symbol. Second, we should be able to check the membership of a vertex pair probabilistically. We resolve the first issue by introducing the in-transition symbol, denoted bot. And we'll resolve the second issue by encoding a vertex pair by an error-correcting code and apply PCP of proximity. assignment testers. Specifically, we use a PCPP for the language LG consisting of the encoding of all edges of graph G. Finally, I will give an overview of our PCRP system. Each proof in the reconfiguration sequence consists of F, G, and pi. Fg is supposed to be the encoding of two vertices of G, and pi is an alleged proof that Fg is in the language LG, which is checked by PCPP. In step 1, we check if F or G is close to code words by using the local tester. If the local tester rejects, then we reject. By this step, F and G cannot be far from code words. In step 2, we check if F or G contains many bots by using random sampling. If F or G contains many bots, then we accept immediately. By this step, we can transform encoding of X and Y1 into the encoding of X and Y2 via encoding of X and bots. And if F or G consists only of bots, then the proof pi can be arbitrarily modified. In step 3, we use the PCPP to check if F and G is in the language LG. And we accept if and only if PCPP accepts. Since F and G contains a small number of bots, pi must be a correct proof. This is an overview of PCRP for succinct graph reachability. In this paper, we developed probabilistically checkable reconfiguration proofs as a new PCP-like characterization of p-space. As applications, we can prove p-space hardness of approximating many reconfiguration problems and resolve reconfiguration inapproximability hypothesis and force over problem of Ito domain Harvey Papadometriou Sideri Uehara Uno. And the interesting question is to apply PCRPs to table games, which have been used in the context of proof complexity. For now, p-space hardness of additive approximation is known. Thank you for listening.